summer, the coast of Cornwall attracts hundreds of people and loads of pleasure boats. Today, these waters look peaceful. But the weather can change, making the sea dangerous and unpredictable. Even modern ships with sophisticated navigation equipment can end up on the rocks. Most shipwrecks sink to the seabed and are lost forever. Undersea adventures take people diving in search of wrecks. But how do they know where to dive?
This is the most important piece of equipment we use. It's a magnetometer. It detects magnetic metals under the sea, and that's usually enough for us to find a shipwreck.
A magnetometer is an extremely sensitive type of metal detector which only detects magnetic metals like iron or steel. The display is usually a straight line. But when a steel-headed hammer is brought close to the magnetometer, the reading immediately changes. Today, Richard is taking some divers to find the remains of a cargo ship called the Saint-Chamond. It sank over 80 years ago. The magnetometer is placed overboard when the crew think they're near the wreck. Then it's towed behind the boat to help find the ship's exact location. If there's a lot of metal, like a ship, the magnetometer can sense it over quite a distance.
There's a reading. We're right over the wreck now.
Anchors away, and it's time to go and explore. But after 80 years, what will remain of the ship and its cargo? The divers descend into the murky depths. Eventually, what's left of the wreck becomes visible. The ship was transporting steam trains from Glasgow to France when it was torpedoed in the First World War. These metal structures are all that's left. The rest has been smashed to pieces by storm after storm. A magnetometer is a useful tool, but it only detects magnetic materials. Back on dry land, how would you tell if something is magnetic? To find out which of these objects are magnetic, all you need is a magnet. There's an invisible force of attraction between a magnet and anything that's magnetic. They're all metals. The huge magnet in a scrapyard makes use of its powerful force of attraction. But are all metals magnetic? See what happens when the magnet is held over an aluminium bike frame or a copper boiler. How about lead piping? None of these are attracted by the magnet. It only lifts objects like this steel drum that contain iron. So, what will happen as the magnet sweeps over this assortment of cans? Some are made of aluminium, the rest are made of steel. Which does the magnet lift? The invisible force of a magnet acts over quite a distance. These tiny round magnets are all holding each other together. Their force of attraction is very strong. So how can magnets pick up objects without even touching? The answer is that all magnets are surrounded by an invisible magnetic force field. This liquid-filled chamber contains iron filings. Place a magnet in the middle and you can start to see where the force field exists. It attracts the iron filings from quite a distance. They're held in space by the magnetic field. Any magnetic object within this invisible field will be affected by the magnet. A computer scanning system makes the magnetic force field even more visible. As the scanner passes over the surface of this bar magnet, the computer plots a map of its force field. The strength of the field isn't the same all over, which is why you see a pattern of colour. Scan a ring magnet and the force field changes. Different shaped magnets have different shaped magnetic fields. Back to the bar magnet, and another image makes the field's strength even more obvious. The bigger the peak or trough, the stronger the magnetic field. For a bar magnet, the size of the field at both ends is equal but opposite. These are known as the poles. There's a north-seeking pole and a south-seeking pole. They're called this because when you suspend a bar magnet in mid-air, the red north-seeking pole will always point north. Bring another magnet close to it and sometimes the poles repel. Other times the poles attract. These magnets are repelling each other. One pushes the other away. The rule to remember is that two north or two south poles always repel, but opposite poles always attract. So what's holding these ring magnets in mid-air? Magnetic forces have been known about for a very long time. According to Greek legend, magnetism was first discovered by a shepherd when his feet suddenly stuck to the ground. The iron nails in his sandals had become attracted to a magnetic rock. This curious stone became known as magnetite, after Magnesia, where it was found. But it was also known as lodestone and was highly prized because of its attractive properties. In ancient Egypt, magnetic repulsion was used to play tricks.
And nothing up my other sleeve. Ha! Ha! Hey, ha!
Objects of worship were made to float in mid-air by the use of carefully placed magnets.
Goes right across.
The first emperor of China used magnetic forces to protect his palace. Legend has it that the gates were made from lodestone.
Lodestone. Come on! Come on! Outrageous. Is that his bottom? What? Is he waving his...
Attacking enemies wearing iron armour were completely flummoxed when they were instantly attracted to the gate and got no further. And this is a small lump of lodestone. Like any metal ore, it's found in the ground. The scanner reveals its natural magnetic field. For centuries, lodestone was our only type of magnet. Take a look at these, magnets strong enough to attract each other through flesh and bone. In fact, they're so strong, you've got to be careful not to get your fingers trapped because their force of attraction is enough to break your finger. High-strength magnets like these have only been around for the past 20 years or so, but more normal-strength magnets have been manufactured for centuries. Shaw's in Sheffield is the oldest existing magnet makers in the UK, maybe even the world. Over 200 years ago, they started making magnets in a tiny workshop not very far from here, and the whole process was shrouded in mystery. First, the workers made bars of iron into the correct size and shape. Then took them upstairs to a special room. It was here that the bars were magnetised. But the workers weren't allowed inside, so they never knew how this secret process took place. Several hours later, the bars would be ready for collection, now mysteriously magnetic. Unfortunately, if anyone had been brave enough to take a peek inside, they'd have been sorely disappointed. This is all they would have seen. The pieces of metal were made into magnets simply by stroking them against an already existing big magnet. In fact, this is one of the secret magnets that Shaw's used. The question is, though, where did this come from in the first place? Well, one theory is, to make a piece of metal into a magnet, it would be heated up, pointed north, and gently tapped. To make this nail magnetic, you'd need to heat it, then line it up with a compass and start tapping. So how does it work? Well, the Earth itself behaves like a magnet. It's surrounded by an invisible magnetic field with its own north and south poles. A compass needle lines up with these field lines and points towards the Earth's magnetic north. Lining up the nail with the Earth's magnetic field is the key to making it into a magnet. That's because you can think of a nail as having millions of tiny magnets inside it, all pointing in different directions. Tapping jiggles them and helps them line up with the Earth's invisible force field. When all the tiny magnets are pointing in the same direction, the whole nail becomes a magnet. It's time-consuming and very fiddly. Thankfully, there's a much easier way. This nail is definitely not a magnet. Here, let me show you. The easiest way to magnetise it is by taking a ready-made magnet and stroking it along the length of the nail, but always making sure that you do it in exactly the same direction. Now, watch this. See? Once again, the tiny magnets inside the nail are all jumbled. But stroking it with a ready-made magnet makes them line up. A quicker way of magnetising the nail uses electricity. Wrapping wire around it and passing an electric current through it has a magnetising effect. This is an electromagnet. The scanner makes the magnetism visible. The arrows show that an electric current through a coil of wire produces a magnetic field. See how similar it is to the pattern produced by a bar magnet. But the field produced by electricity through the coil is weaker. If the coil is big enough and the electric current is high enough, then the piece of metal will stay permanently magnetised. Take a look at this. There you have it. This factory uses electricity to make hundreds of permanent magnets every day. But what are they made from? Iron isn't good enough on its own, so they mix it with other metals, including nickel and cobalt. Any mixture of metals is known as an alloy. In the foundry, this alloy is heated up to 1600 degrees Celsius before being poured into a mould. One mould makes about 20 horseshoe magnets. The first stage of magnetisation involves heating up the metal shapes again, then cooling them down in a strong magnetic field produced by the massive coils of wire that make up this platform. The electric field has a magnetising effect. Once they're painted, they're packaged up. The permanent magnets they make here go all over the world and end up in all sorts of places. So where do you find magnets today, and what are they used for?
And that's coming up after this.
96.3.
RFM lead.
As a radio DJ, I'm surrounded by permanent magnets all the time. Like this one here, found in my headphones, and these found in the big speakers. And there's even one in this microphone.
And would you believe there's a link between cows and magnets, as our vet explains.
The cow magnet will sit in the front stomach of the cow, where it can attract hazardous pieces of metal, like this bit here, which the cow may eat by mistake. While this piece of metal can roam free in the cow's stomach, it could puncture the stomach wall and cause the cow a lot of harm. But while it remains attached to the magnet, it can cause no harm at all.
Permanent magnets are useful, but sometimes you need a magnet that can be controlled. A magnet that can be switched on and off, like the one at the scrapyard. It helps them move bits of metal from one place to another. Doctors use temporary magnets too.
As an eye surgeon, sometimes we have to remove tiny bits of metal which become embedded in the backs of people's eyes. And if you look at this X-ray, you can see this tiny little fragment here at the back of this person's eye, and this could cause serious damage. And we remove those fragments using an electromagnet like this one. Now here we see with the electromagnet off, it's not able to lift up a bit of metal like this paperclip, but if I turn the magnet on, we're able to lift up that paperclip. And that's how, as an eye surgeon, we use electromagnets to remove bits of metal from the eye.
Magnetism gets everywhere. There's a magnet in anything that has a motor, like your hairdryer or the microwave. There's a magnet in your telephone, in a computer, in a video recorder, and your TV. They do a lot more than just hold notes to your fridge. Magnetism affects your life more than you think.